In this module, we will again talk about the media formulation, but in this module, we will talk about some factors in another way. So, as concerns reported by Kone in 1979, while calculating the theoretical yield of penicillin G on the base of the material and the energy balance using biosynthetic pathway based upon the stoichiometry reaction. So, the stoichiometry equation reported by Kone 1979, you can see here that glucose A2, in this whole equation you can see that A2, B2, C2, D2, E2, N2, P2 and Q2, these are the different stoichiometric coefficient, and in this equation that PAA is phenylacetic acid. You can see in this that first one is glucose and other is ammonia, and then is oxygen, then sulfuric acid, and then I have already told you that phenylacetic acid, and this one is this is basically the medium, and then lead to the production of penicillin G, and then the release of carbon dioxide and the water. This is the production. So, if we see this equation that if we know the stoichiometric coefficient, then we can hypothetically calculate the yield of penicillin by this equation. So, as concern the solution of this equation, so if we calculate that 10/6 glucose and 2 molecules of NH3 and half molecule of oxygen and 1 mole of sulfuric acid and PAA, phenylacetic acid, so then that lead to penicillin G, carbon dioxide and 9 mole of that. So, in this instance it was calculated that the theoretical yield, that 1.1 gram of penicillin required 1 gram of glucose. So, 1.1 gram of penicillin, in other terms we can say that it is 1837 unit per milligram. So, 1 milligram of penicillin having the unit of 1837. So, 1.1 gram penicillin that can be produced by 1 gram. This is the hypothetical yield of penicillin G. So, the other major nutrient which will be required is oxygen, which is provided just by the aeration of the culture. You can see in this that the major part of this production is glucose, and then is oxygen. So, oxygen mostly, as you can see, I have mentioned in this slide that is mostly fulfilled by aeration in the culture, proper aeration and agitation method that can fulfill the oxygen need. In later chapters we will talk about the importance of aeration and agitation, and that what are the factors that affect on the dissolved oxygen, that's very critical, and the supply of oxygen, and ultimately on the product formation. So, as we have seen that oxygen is very critical. So, oxygen in the medium design is very critical. When there is a more reduced form of carbon in the medium, then that require a higher amount of oxygen. As an example, if we have a two choice, one choice is a glucose in the medium, and on the other hand, if the carbon source is N-alkane. So, if we look in the chemical composition of N-alkane, that have a more carbon, and then as compared to the glucose. So, if we use N-alkane, and then there should be more oxygen supply in the medium as compared to the glucose. So, the oxygen demand with respect to the higher reduced form of the carbon increased. So, we have to be very careful about the oxygen demand and the utilization of the carbon source in the fermentation medium.